Welcome to the topic of number system and conversion. It's a very important topic in computer science competitive exams, and its understanding is required for the subjects like computer architecture and organization, digital logic, microprocessors, assembly language, and even in networking applications. Now, the number system which we will cover in this video is hexadecimal number system. So what are hexadecimal numbers? But before that, I would like to see some applications where computer represent the information in form of hexadecimal numbers. So first example is the C language program. Here we want to print the memory address of a given variable, and when the output comes it looks like this. So a is the name of our variable, and we have printed the address. This symbol means address of a, and this is basically a 12 digit hexa code, and 0x in C tells that this is a hexadecimal number. Now, if I ask you to check your Internet Protocol version 6 address in your internet settings on a Windows or a laptop or PC, you will get to see this type of big number which is made up of 32 hexadigits. So this is also an hexadecimal number. And if you see some of your design application, or you visit some website like this, it gives us this is the color shade which you want to use in paintbrush or Photoshop or even in HTML. You can use this decimal coding, RGB coding, because we know that there are three primary colors, red, green, blue, and they each of them have 256 shades. Or we can use this hexadecimal code, which is made up of 6 hexa digits, and they start with the hash sign. So one common thing about all these numbers are that they are made up of some digits as well as some alphabets. So we will revisit these examples at the end after we have discussed the basics of hexadecimal numbers. So it is a base 16 number system, and secondly, it is a positional number system. What is meant by base 16? It has 16 unique symbols. Base, or it is also called radix. What it tells, it represents the total number of unique symbols in a given number system. So what are those numbers in hexadecimal? Well, in hexa, those numbers start from 0, then it will continue till up till 9. After 9, what should I go for after 9? Because after 9, I'm no more left with any single unique digit number. So for the remaining 6 characters, English alphabet characters have been selected to maintain the uniqueness of the symbols. So there are 0 to 9, 10 digits, and then there are 6 alphabetic characters from A to F, and together they form 16 symbols. Right? Now, question arises, what is the numerical significance of these numbers? But let's complete this part first. How to identify whether a given number is hexa number? So once you start up with the conversions, you will have to represent hexadecimal numbers. So one is like in this case, H subscript is given. In this case, I can easily identify that this is a hexa number because it has got valid hexa alphabets. But in this case, 2 and 3, this can be slightly confusing if base is not mentioned, because it can be a decimal number, it can be octal or hexadecimal. 1 and 0 can appear in all the 4 number system. But once you put that subscript 16, things become very clear that these are hexadecimal numbers. So subscript 16 can be used, especially when we are working with the conversions. So these were all the 16 hexadecimal numbers from 0 to 9, and then from A to F. But what about the decimal equivalent? So before that, let us see in our calculator. And this is the program calculator in Windows, and this is, you have to select this programmer option, and you will find all the number systems appearing over here: hexa, decimal, octal, and binary. If you select any of the number in any number system, it will show me the equivalent number in its equivalent number in other number systems also. So let us suppose we select hexa and this A, B, C, D, E, F alphabets are also appearing over here. Suppose I write A. I want to know what is the decimal equivalent of hexa alphabet A. So hexa it is A, in decimal it is 10. It is equivalent to the quantity 10 in decimal number system. In octal it is 12, and in binary this is some 4-bit binary code 1010, and we know that this is the code of 10. But what about the hexa alphabet, let's say 1, right? So in hexa it is 1, in decimal it is also 1, in octal also it is 1, but in binary it is this 4 bits 0001. Otherwise, when we write binary in just pure form we just write only 1. But when you are writing its binary, the hexa, you are given the hexa number 1 and you have to find its binary equivalent, it will be written using 4 bits, right? So we have some decimal number equivalent. Let us see that. That decimal equivalent start from 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. That means for the first 10 symbols, the decimal representation and hexa representation is same. So if I have 9 in hexa, it will represent 9 in, it will be equivalent to 9 in decimal. But if I write A in hexa, what decimal quantity it will be equivalent to? So after this is going in a running order, right? It's in a running sequence. So after 9 comes 10, 10 after 10, 11, 12, 13, 14 and so this is equivalent to 10 in, A is equivalent to 10 in a decimal number system, and F in hexa is equivalent to the quantity 15 in decimal number system. Where do I need these equivalents? When we will do the calculations, so some number is given to you and you are asked to multiply this number with some power of, let us suppose with power of 16, and I can multiply f directly with this power of 16. So I will be using the decimal equivalents, right? So decimal equivalents are very easy to remember. They are just continuous running number from 0 to 15. That is clear. Now question arises, like when we were seeing that calculator, we were also seeing the octal equivalent and we were also looking at the binary equivalent. So in this video I won't be discussing the octal equivalent, but we will discuss the binary equivalent. And first let's see the calculator. You see that when hexa 1 is written, that binary equivalent is coming to be 4 bits 0001. So for binary numbers, first of all, let's see this. These are the decimal equivalents. Now for binary numbers, if you see, this formula will work. That is 2 to the power of 4 is 16, right? 2 to the power of 4 is 16. 16 is power of 2. So what should be the power over here? It is 4. So that will give me 16. So every binary number is formed from the combination of 4 bits when it represents a corresponding hexa number. Suppose I have this hexa number F. I want to find out its binary equivalent. It will be represented using 4 bits. Similarly, if I have this binary hexa number 16, it will be represented using 4 bits. So there is, we will see first the complete chart. So this is the complete chart for all the initial 15 numbers. There are several ways to draw up this chart. If you're familiar with binary addition, see 6 code is this, you add 1, you will get 7 and then 8 and then 9 and 10. But if you have to quickly derive the binary equivalent of any given hexa number, you can follow this sum of weight methods. So what does that mean? Let us see. So this is our basis 2 and weights of first 4 binary numbers. Now I have this value A in hexa. Its decimal equivalent is 10 in decimal. And if you see here, which numbers weights add up to give me that 10. So it is 8 plus 2. So put 1 under 8 and weight, and then put 1 under this weight 2, and for the remaining weights put 0. If I have this number 2 in hexa, it is also 2 in decimal, and this is 2, right? Other weights won't contribute to anything to it, so we'll put 0 on this side, but we will also put this 0. So actually this is 2, but we know that we have to put 4 zeros. So in this way, using this method, you can find binary equivalent of any of the hexa digit from 0 to f. Where do you find it useful? Because whenever we will go for calculations purpose, conversion purpose in our subsequent videos, this foundation is going to work over there. Now, what are these conversions? First of all, let's see, revisit our calculator. What it was doing, see, I wrote the hexa 1, and then it gave me its decimal equivalent also, octal equivalent also, and binary equivalent also. So that was, it was doing some conversions. Now, if I click on hexa and I write 2-digit number, FF. So what is its decimal equivalent? That is 255. And this is its binary equivalent, because one hexa digit needs 4 bits for representation. So 8 bits for 2 hexa digits. So this is hexa number. This is its decimal equivalent. So see, using 2-digit hexa code, we can represent decimal values up till 255, right? And that is something which we will understand when we learn the counting in hexadecimal number system. But what is actually it is doing? It is doing conversions, but you can't use the calculator every time, especially in exams. So, and moreover, if I just use this calculator, I will not get familiar with the mathematical principles behind this these type of calculations. So, we will learn different type of conversions. Now, I have this hexadecimal number, suppose 10 in hexa, and what is we have to find out its binary equivalent, octal equivalent, decimal equivalent. Or I have given a number, binary number, octal number, decimal number, and you have to convert it into its hexadecimal equivalent. Okay, what does this 10 means in hexadecimal number? Let's see in our calculator before we understand the manual procedure. So if I write here 10, I've selected hex over there. So 10, this is 10 in hex. This is equivalent to 20 in octal, and this is the binary code. But what is it? What value it represents the quantity? 16, right? So that we will understand when we become familiar with the counting process of hexadecimal numbers. Positional number system. So for conversions, we must also know the positional, the weights which are assigned to the digits according to the its position in the number. So like binary, every number system is a weighted number or a positional number system. So position of each digit will indicate the magnitude of the quantity represented, and it is assigned a weight. So weights are power of 16. So let us suppose I have this number. This is least significant digit, most significant digit. This is only whole number. And let us consider this fractional portion. Let it be a separate number. So this is our hexadecimal point. This is most significant digit. This is least significant digit. If I just take this fractional number, in this case, we will write the powers of 16 for all of these numbers. But for the whole number part, our powers will start from 0, from least significant digit. Then I'll move towards most significant digit. So our powers are positive powers of, they are positive powers and they are increasing. They will start from 16 to the power of 0. For fractional for fractional power, these are negative powers and they are decreasing. We start from this most significant digit and we will move towards least significant digit. But if it's a mixed number, it's a combined number, 2FB hexadecimal point FF, then this becomes your least significant digit and most significant digit. 2 is the most significant digit in this case. Now you can start writing your powers from here also, but if it is a long fraction, then you must be very careful in writing that the last number in the sequence, otherwise things can go wrong. So better way is write in this direction first and this direction. So write first all the weights for the whole number part, then write weights for the fraction part. Now, if you read, this is your whole radix point. If you read the numbers from this point onward, you will see that -2, -1, 0, 1, 2. What is happening? Our powers are increasing as we move towards the most significant digit. So you can just have a look at it. So positive powers for whole number, negative powers for the fraction part. Negative powers are decreasing and positive powers will increase depending upon that we are starting from 16 to the power of 0. So these are some of the weights which you can remember. So if I have a 6-digit code, as we saw in our color code, so each of these number will have the weight. When we learn the conversions, we will try to see because in colors, this color code basically stands for white, and that is the maximum color. And we also know that uh, there are about 16 million colors which can be formed by the combination of 256 shades of red, 256 shades of green, and 256 shades of blue. So we'll just see that in a minute whether this number, 6-digit number, it comes out to be 16 million in when I express that value in terms of that decimal number system. But these are some of the calculations which we must remember so that our calculations become quick when we are going for manual method. So why need hexadecimal number? So we have seen its application in C language, in networking applications, in color codes, in microprocessor, in assembly language, right? So one benefit of using the hexadecimal number is that it offers a compact representation of long binary strings. We know that computer internally handles the data in form of bits, zeros and ones, but if that bit representation is shown to the user may have difficulty in handling those bits because that bit long binary string is not human friendly, while these hexa numbers can represent data in human friendly format. What do that mean? So let us revisit our examples. This was our C example, and this was our address part. It is made up of 12 hexa digits. So I had put this number in our calculator. So this is my hexa number. This is some decimal equivalent. And if you see this binary string, which computer understands, it is made up of 42 bits because 12 into 4 is 48 bits. It becomes 48 bits. Right now, if suppose C language shows you this string and you were to write this string somewhere, you will soon lose the track of writing the bits because you will start mixing up zeros with ones, and you may drop out certain bits, or you may end up writing some extra bits. So this number is easier to report rather than this number. In this case example, so FFFF, so I just told you its decimal equivalent, just see it's coming as this number, 16 million almost. That is the maximum color shade. That is why we say that there are about 16 million shades that can be formed by the 256 shades each of red, green, blue, and the maximum color code is FF, and that is this is 255, 255, 255, red, green, blue, and that forms the shade white because maximum color code has been mixed and equal quantity, so it forms the white color. And this 6 hexadigit code is translated into 24 bits. So imagine writing this bit string in your HTML code, it will get confusing. What about this number? That was 32 hexadigit. My calculator would not support this, so there are certain uh, websites which offer you hexadecimal calculator. You can just put this number over there and just omit out this colon part because colon is not the part of our hexadecimal number system, and you will get this bits. If I ask you to count how many bits, okay, that will keep, if you start counting manually, it will start taking time. So 32 into 4, simple, 128 bits. Why 4? Because every hexadigit is represented using 4 binary bits. So if you see this, these are 4 hexadigits. So 4 hexadigits will get translated into 16 bits. So this section, so 4, 1, this code is 2, and this 4, 4, 4, it is 0, and this is also 0, and this is 1, right? So if now all of a sudden computer shows you this format, it will be difficult for us humans to handle such a long binary string. We, if we were to write this code, we are bound to commit some mistakes. So this is human friendly format, and this is computer friendly format. So thanks for viewing. If you have understood the topic, you can subscribe, like, and share with your friends. I'll see you in the next video. Till then, take care. Thank you, and bye-bye.